I've made this vacuum cleaner auto switch. So when I'm operating the circular saw, the vacuum cleaner is switched on and sucks away most of the dust. When I've completed sawing, the cleaner is switched off after a delay. So let's now go back in time and I'll show you the details of how it works and everything. So this is the box before I've screwed it onto the workbench. This is so I can show inside and talk you through how it's all working. So as an alternative to a saw, I've got a couple of table lamps. So this is a saw, this is a vacuum cleaner. So the powering comes here, and this is the power socket for the saw, and this is the power socket for the vacuum cleaner. So if I turn on my saw, the vacuum cleaner comes on. Turn off my saw, the vacuum cleaner goes off after a 30-second delay. The delay has two functions. Delay there is so I can switch the saw on and off, and the vacuum cleaner doesn't keep power cycling to match the saw, and also it helps clear its tubes. The button on the front has three functions. You press it once, turn the vacuum cleaner on, press it again, and that'll switch it off after the 30-second delay. If you press it, so there's two beeps after a delay. 1, 2. So if I now turn on the saw, the vacuum cleaner stays off. To reset, press it again, and that sets it back to how it's supposed to work. The third option on the button, let's wait for it to go off. So beep once, beep twice, beep 3 times, let go, and that causes it to reset. So it plays its reset tune, and that's it. That is as an alternative to unplugging it and plugging it back in. So I've got 3 indicator LEDs, because LEDs. First one just shows that it's plugged in and the microcontroller is doing its thing. That one's to show you that your vacuum cleaner's on, because you might not hear it or something. And this one is to show that the monitor for the power off is active. I think that's it for the outsides. I'll have a look on the insides now. Inside we have the current detector, we have the microcontroller, we have the annoying beeper. This is the FTDI connector, so I can program it and monitor a serial if I need to. It's on strip board and it's all glued down with a couple of blobs of snot glue. On this cable through there to the other side, we've got the relay, and down here we have a USB power supply. Well, we have a modified power supply, USB power supply, which gives us 5 volts to the microcontroller. The power supply came from one of these little these main sockets with a USB charger built into it. I've tried to insulate everything away from the mains cable, so I've used these click connectors, so it's quite difficult to actually get exposed wiring. I don't like that there, that's exposed. I'm not keen on that. So the mains wiring, power in, so that's through the main socket I showed you earlier, and that goes straight through the current sensing thing out to the mains power socket on this side here. So that's for the circular saw. So the next row down is the relay module. Again, this is wired before the current sensor, and that goes out to the switch socket there. So it's only the live or line that's switched. Also tapped off the same part of that circuit as the USB power supply. Oh yes, the microcontroller is an Arduino Mini R5. It's a discontinued board, and unlike, let's say, a Wemos, he said, picking one at random, this was 5 volt tolerant, so the current sensors work at 5 volts. They give an output relative to the 5 volts, so if you saturate the output, then the output is going to be 5 volts. So if you've got using a microcontroller that isn't 5 volt tolerant, let's say a Teensy or something, then you might knacker up your board. You need, I think, a voltage divider. Mains electricity, be careful, don't get yourself electrocuted. It's not nice, and you can end up dying and things. Okay, so that's the electrics. On the electronics, the wiring for each part, nothing special. Every Google search will show you this sort of push button layout. There's a little 0.1 UF for the FTDI connector. I think that's standard, that's expected. Bring the LEDs, because these are quite old ones, have 220 ohm resistors. I think if you're using some fancy modern ones, you can have higher resistors in. Just select one that looks nice, the brightness that you want. So the D there indicates the connection to the Arduino, to the microcontroller. Again, the relay module, that's just the connections on the underside of the little board that it shows you. The piezo buzzer goes through a little transistor just to make sure it can, I don't overload it or anything. Overload the Arduino, sorry, by pulling so much current. Current sensor provides an analog output, so that's analog to the controller at 5 volts. Yeah, there's different types of current sensors. I've actually got 2 different types here. These 2 came off eBay, and this one came from some online shop. This is the older model, the ACS 712, and this one uses the newer ACS 723. The 712 is kind of considered obsolete, but they are cheap. I don't like the PCB design, so you can see that on this one here there's a tiny gap between the ground plane, which connects to the ground on your Arduino. So I modified this one to remove the ground plane and hopefully improve the separation. I'm going to kind of ignore this one now because I've got the 723, and you can see also that the PCB, the printed circuit board, is substantially better. They've got proper isolation between the ground, between the data side and the mains voltage side. On the data sheet for this particular chip, will work up to 65 amps continuously and have a maximum working current of 297 volts. I don't know how this PCB would be able to handle that sort of current, so I'm going to assume that it won't. This is never going to see anything more than 13 amps, and normal use would be 5 or 6 amps. But this is the 5 amp version of the chip, so that means that if I drew above 5 amps, then the output pin here becomes saturated and will give a 5 volt output. That's the downside of using a 5 amp chip. So let's say this one's the 20 amp equivalent, then if you're drawing 8 amps with the 20 amp version, you would still get a measurable voltage, whereas with this one you wouldn't. However, because the sensitivity changes per version, so if you've got the 20 amp version of this, it wouldn't be as sensitive, so smaller changes wouldn't be measured. So you've got, let's say, a bad example, because even this chip struggles to see this. This is a 48 milliamp LED bulb. It can't see that you've switched it on because the bulb simply doesn't draw enough current to make a big enough difference. So, but I'm not interested in measuring the current, I just want to see that a current is being drawn. This one for me is fine. So this is a software. I'm not going to explain it because the video is already getting too long. I'll put it up onto a GitHub and you can get it from there. I'll add more comments and things to make sure that it's all readable and everything. So I now need to attach this to my bench and use it. Yeah. Well, thanks for watching.